Welcome to this pre-recording of lecture 16 of a course in Introduction to Supercomputing. So in this course we have started with high-level parallel processing, then looked into distributed memory parallel computing, shared memory parallel computing, and now accelerated parallel computing. So these are kind of the three pillars for high performance computing or supercomputing. So in the lecture of today, I will start this third type of technology and introducing the differences between central processor unit, the CPU, and the graphics processing unit. So the title of the first section is the general purpose GPU. So general purpose to make somehow the distinction with the graphics processing tasks. The main conclusion of this lecture is that there is a lot of performance to be gained. However, the programming model depends on data parallelism. So that's fundamentally different from what is typically introduced. However, one could argue that because of the performance gains, that the data parallel view of computing should actually be very much be just as considered as general as parallel computing is. Okay, so let me go in. So this is the massively parallel processor. So every computer comes with a GPU, and we are actually very much oriented towards visual problems. So whenever you buy a computer, its graphics processing unit is actually the one that is often improved the most. So also memory bandwidth is an important problem. So a lot of problems are memory bound, and you already gain a lot of speed up just by the fact that the memory bandwidth of graphics processing units is typically one order of magnitude higher than that of the common central processing units. So in some sense, this is also labeled as personal supercomputing. So there are high-end gaming laptops, and these high-end gaming laptops, they have processors that come very close to teraflop performance. And there are also examples and actual applications. So there is the MRI application that is mentioned here to process images in real time. Okay, so I will follow the textbook that is listed here. So I have the textbook, so let me pull it over. So this is the cover. So I have also the first and the second edition. So the book is already more than 10 years. Second edition is actually in its 10th year anniversary. The area is evolving extremely rapidly. So, but still the book covers many of the most fundamental topics in data parallel algorithms. So there's a lot of terminology on this slide. So CUDA stands for Compute unified device architecture. The unified is a little bit misleading, although NVIDIA is certainly dominating the market of high-end graphics processing units. Others may, of course, disagree with this. But a lot of so in next week we will get into programming the GPU. I will be mainly focused on the programming model that is provided by NVIDIA. So, another topic is that there are already many high-level environments to do GPU programming. However, the benefit, and you can see we have the thread organization, the memory movements. The advantage of looking into that in detail gives you a better appreciation how the hardware works. So most of the evolution with programming has been moving away from the certainly with managed memory, so the programmer can write very nice and can be very productive without having to worry where the data is in memory and what type of memory is being used for what type of computation. The GPU programmer, if you really want to go for performance, then the GPU programmer has actually access to all of that. So in some sense, it will get at times quite technical, but it pays off. So there's a lot of insight to be gained in reasoning with the hardware in mind. Okay, so this is an introductory course in supercomputing. One can spend certainly one entire semester course on GPU computing. So we unfortunately do not have the time for this. So the purpose of this lecture and the next 6 ones is kind of to give a flavor of with the goal of understanding. So as before, so the most convenient and often very effective way to do supercomputing is to apply existing software libraries that have been optimized and customized to accelerate certain types of applications. So in the benefit of this course is that you kind of will get the understanding of should you accelerate your own software, or should you actually look for an existing package. Now, every major scientific computing application has been accelerated already. One can also turn it around. If you don't find an accelerated GPU accelerated versions for certain types of computation, it might be an opportunity for you, but might also be an indication that that type of computation is actually not that useful for science. Okay, so we have some expectations, mainly the understanding. Not all problems benefit from GPU acceleration. So this is massive parallelism, and one needs to think of a very, very fine-grained level of parallelism. So I mentioned already, should you develop your own code? Might be very good, but might not be so good if you want to solve an application. In the first runs of the course, GPU acceleration was a third topic towards the end of the course. Now I've shifted this before the midterm exam, so before the middle of the course. And this is to allow for an opportunity to mix message passing, multi-core, and GPU acceleration. So every computer is connected to the internet. Every computer has a multi-core processor and has a graphics card. So in some sense, the question of combining several computers, of using the multi-core, using the graphics processors, already hints back to the personal supercomputing. So it could still be that there is a lot of the application code that is sequential, but what GPU accelerators can do is they can, when you identify the computational bottlenecks, then with customized and highly efficient GPU code, you can dramatically improve the performance of the software to solve a particular application. All right. So our extreme supercomputer at UIC has several nodes with Pascal GPUs, which are not accessible for educational use, but I have on my office desk micro workstation with Pascal P100 GPU. The double precision floating point performance is 4.7 teraflops. So there's often a misunderstanding that when you use GPUs, you have to limit your precision to a single float, not double float, or even half a float. But that can be done, but that's not necessarily. So one can, and I hope to explain this later in the course, one can compute very accurately with GPUs. And my personal motivation of using GPUs is to compensate for the cost overhead. So here are the full specifications. And so trying to kind of compare the 22 cores with the GPU, the top performance that you would get, so there is a very simple computation here, would be 700 gigaflops if you are using all cores to the max. And perhaps this can go to teraflops if hyperthreading is fully exploited. But then still, you would most likely not match the performance of the Pascal GPU. So I mentioned the Compute Unified Device Architecture. So if you buy an NVIDIA GPU, then the software development kit comes for free. And Microwave is a company that provides turnkey computers. Just have to press the power button, and there it goes. You're ready to start doing supercomputing. Okay, I have access also to a Volta accelerator that was purchased shortly before the pandemic, and which I was managed to quarantine at home, still at home. So you can see the evolution. The bottom line is that the performance went from 4.7 teraflops to 7.9 teraflops. What I didn't list here are my earlier graphics cards. So Kepler had a theoretical performance of 1 teraflops. But achieving that was kind of hard because there were not as many streaming multiprocessors available. So I'm going a little bit too fast here. So let me try to explain the core count. So there is an analogy with processors. So you have multiprocessors that have multiple threads, that can handle multiple threads. So, however, with the analogy often is that with between GPUs and CPUs, that GPUs have streaming multiprocessors. So the numbers for Pascal is 56, for Volta it is 80. So any streaming multiprocessor can independently execute instructions. But every streaming multiprocessor has multiple cores. So this is instruction level parallelism. And in both cases, it works best if you can organize your computations such that 64 threads or multiples of that, 64 threads, typically multiple of 32, 64 threads actually execute the same instruction. So the CUDA core count is the multiplication of the streaming multiprocessors times the number of cores per streaming multiprocessor. And you see that in going from Pascal to Volta, it nearly doubled. So this has been looking at compute-bound problems. What I like to do, if you are using multiple double arithmetic, then you get into the compute-bound side, and that's very attractive. But also, I mentioned the memory-bound computations. You see that there is also benefit from Volta over Pascal. So the peak bandwidth actually went up, and almost to the terabyte per second peak bandwidth. Okay, so where do you find documentation? So there's a lot of free reading that can be done. So the information on the next slide is taken from the last white paper on the Hopper architecture. So I listed the Pascal, the P100, and the Volta, some aspects, some major specifications on the previous slide. So these architectures are 5 to 6 years old already. The current newest GPUs are called Ampere and Hopper. So here is the evolution of the bandwidth. So there was not that much difference, if you like, between Pascal and Volta, but Ampere significantly improved this, certainly if you compare it with respect to Pascal. But then going from Ampere to Hopper actually goes to twice as much. And if you go to the websites of NVIDIA, which I would encourage you to look at the white papers in detail, then you will see that the advertisement is for artificial intelligence. So a lot of applications are actually memory bound and benefit a lot from this increased bandwidth. And you see that the units are actually already expressed with terabyte performance. So when we think of floating point performance now in terms of GPUs, we have teraflop performance, but also we have teraflop performance in terms of the bandwidth. So this is kind of the conclusion of the slide. Here are some details of the evolution. So the previous slides compared Pascal to Volta. Here I copied this from the white paper on the Hopper, so you can see the core count. So you can see that I'm interested essentially in the 64-bit floating point computation, so the FP64. So going from Ampere to Hopper, it actually doubled. So again, this means that if your computation, if your application is not really parallel, then this will not mean much. And also the parallelism, as we will get, needs to be really massive. So you have 7,000 cores available at you, and the number of threads that you will have to keep busy is actually a multiple of that. So it's good to keep that in mind. So this is massive parallelism. So you really have a supercomputer on your desk here. This is personal supercomputing. There is the clock speed. So it's still expressed in megahertz, but 1.6 gigahertz is 1600. So CPUs, it's typically 2 point something or 3 point something. So the clock speeds of the recent generations of GPUs cores is already getting very close to the 2 gigahertz. And yeah, and many problems are actually memory bound. Okay, so the evolution, so you could say, well, going from Pascal to Volta, it's actually not even twice. But look what happens if you go from Pascal to Hopper. So 5 or 6 years, you go from 4.7 to 25, and that's quite noticeable. So Moore's law is actually still active if you are having data parallel applications. Okay, so the future is already here. As they say, it's not evenly distributed. Let me step back a little bit. So now I'm actually following more the textbook and give somehow the comparisons between CPUs and GPUs. So this is a historical slide which I lifted from the NVIDIA programming guide. I see one of my earliest graphics cards there, the Tesla C2050, which is also at home. But you see that this was already a card that was better than the single core CPUs. So there are some caveats in this, but still, so comparing a single core against single core CPU against a GPU is completely unfair. So I will give a reference towards the end to mitigate that a little bit. So the Tesla C2050 was my first card. You see the Tesla K20 towards the end there. So these are the high-end graphics cards. So there are two types of graphics cards. The ones that are capable of double precision performance, and the ones that are geared towards more single precision and integers computation. Other comparisons charts. Again, so these are the historical. So kind of to indicate that in the 2000, in the middle of the first decade of the 21st century, there was a noticeable distinction between performance in GPUs and CPUs. One can have the same plots for single core and multi-core. So one can still say that Moore's law is still alive if you consider multi-core processing. Memory bandwidth is actually one of the killer features of GPUs. So most applications, many applications, if not, I wouldn't say most, but many applications are memory bound, and there is a clear benefit already from even if you don't really do much to your software, the fact that the threads can read in much faster the data. If you have the data nicely aligned, there's a but also there. So if everything is nicely organized with your data parallelism, then it goes a lot faster. Bandwidth again. So these are historical slides. A little bit later now, not in the middle of the first decade, but the middle of the second decade of this 21st century. It's still expressed in gigabyte, not yet at terabyte per second. So here are some numbers for the workstation that we can use in this course. So the memory bandwidth for the CPUs is at 76 gigabytes per second. For the Pascal, it's already getting closer to the terabyte per second for the peak bandwidth. So even if you do a straightforward parallel implementation, you often have already a speed up of 10. Now, if your problem is actually memory bound, one should also say that this might be also the limit at what you could get if that is the peak. All right, there is a but now. So any processor core can execute any type of computation. So when we discussed multi-threading and even also multitasking, we were just shifting the granularity. So instead of running programs on processes, where we started with distributed memory, where we were launching different processes on mapping them on different processors. We could sustain that same view more or less with multi-threading and multitasking, even though we had to be a little bit more careful about synchronization issues. But the synchronization issues kind of were mirroring the communication issues that we had with distributed memory passing. So the nice thing about distributed memory and shared memory is that you could still try to maintain the logic a lot. Now, what the picture here actually shows is that at the left, your CPU, so and this would be a 4-core, so we have the arithmetic and logical units of the CPU. And they are very big. So the green blocks there are actually the workers. They are big because they have the same capabilities as any other processor. Now GPUs, we have many more algorithmic and logical units. But they have much smaller caches, much smaller registers, and they actually execute the same instructions at the same time. So that's how GPUs achieve their increase in performance. Now that's it, but as a programmer, often you have to scratch your head a little bit. So it requires often a fundamental rewrite of the logic of your code. And this is also a little bit the purpose of the understanding in this course. You can think of a way of doing computation one particular way. But if you think about it in the data parallel sense, then the picture of the GPU actually starts to make quite sense. Okay, the next lecture will be entirely devoted to the hardware. So we have a GPU. There is hierarchy, so the processors are aligned into arrays. So every array is managed by one streaming multiprocessor. So the streaming multiprocessors, they share the same control logic and the instruction caches. So the reason that the caches can be a lot smaller on GPUs is because they actually all execute the same instruction, but then on different data. So there's also global memory. So there is the hierarchy where every graphics card has its global memory. There is the caches, and then there are the registers. And then there is also the memory of the CPU. So one also actually needs to be very careful. You want to accelerate the computations that happen that the CPU has to do, but the data actually always resides on the CPU. So one needs to be careful about the memory traffic. Otherwise, if there is too much memory traffic, the benefit of GPU computing is will not be noticed. Also, this is massive parallelism. You must have many threads scheduled, many threads that is a multiple of the number of cores. In some sense, this is similar to tasking that we have seen, where we can spawn as many tasks as we deem is necessary. But if you do multi-threading and also multi-processing, you try to map the processes onto the processors you have. The threads, you map them onto the threads that are on the cores. So that there is this logical distinction a little bit that one needs to be careful about. Bottom line, massive parallelism. Okay, here is a picture that I have stolen. So there was the schematic diagram. Here is the picture that I've taken from slides of the course of the textbook that I'm following now. This is the older graphics card with 16 streaming multiprocessors, and that was already capable of half a teraflop, but then most likely single precision. You see the specifications listed, and you see a little bit of the details of the what sits between the CPU, which is called the host, and the GPU, that's called the device. Okay, so here again are the numbers. So the hierarchy of the architecture, the arrays of the cores are steered by the streaming multiprocessors. So one needs to be careful to have sufficiently many threads scheduled, but also not too many. So there are some limits as well. So the notion that is coming here is that of a warp. So there is single, so there is instruction level parallelism, and one can of course have that one. So this is also a misunderstanding sometimes, that you cannot have if statements in GPU code. No, that's not true. You can have that sometimes one thread executes one instruction. That's perfectly fine, but typically for performance, the instructions are organized to be executed in groups of 32. So such a bundle of threads is called a warp. Okay. Programming models. So at this point in the course, we have introduced ourselves to message passing and OpenMP. And here is what the authors write. I don't disagree with this statement, but you may want to, at this point, we are introduced to MPI and OpenMP. Whether we are experienced enough is another matter. But it's another way of thinking, so that's the main part. And changing your way of thinking about code takes time. The programming model, so we started this course with the Flynn classification, and with message passing we were using single program multiple data. Here actually we have single instruction multiple data. So we are using a much finer grained level of parallelism. So warps are blocks of threads that execute the same instruction. And by the same instruction, it also has to be organized such that they read from memory in groups. So the memory has to be aligned properly. They also write to adjacent memory locations. So, and this is again massively parallel. Okay, so single instruction, multiple data. Often it's also called single instruction, multiple thread. So one can have, and one must be flexible in thinking. So there is the data parallelism model, but it needs to be aligned with the instruction level parallelism. Now I mentioned that all important tools in scientific computing are already accelerated. In the last lecture I mentioned the view from Berkeley, that technical report. That technical report identified the dwarfs of scientific computing. So the linear algebra, the Fourier transforms, we will actually study the linear algebra matrix multiplication that has been optimized. So when we were running also Julia, we were running optimized code. So if you have to solve an application, please check what is already available and try to use that. For educational users, we often will look into our own codes. Okay, so there are many alternative computations. So there is the Open API that I mentioned in the previous lecture. I have not listed it here, but that is one of my to-do things. I'm following here the textbook. OpenCL is still a standard for heterogeneous computing, although it may not be so widely supported. There is OpenACC, which is similar to OpenMP, that it uses directives. So in a sense that if your logic in your code is already suitable for data parallelism, then it may be just adding some directives to it to make it run. So this has the major benefit for the correctness. Correctness is an important topic if you start to reshuffling the logic. Okay, so I was listing here more the added features in going from the first edition to the second edition. So the core of the textbook remained the same, but in the meantime there had, in the 3 years between the first and the second edition, many more alternatives to the CUDA programming model are there. Okay, 40 minutes in this lecture and I'm done. So there are plenty of resources. So the main exercise here is that you check out on your own computer what are the specifications of your graphics card and compare it to the specifications of your CPU. Certainly if you have a gaming laptop, your graphics card will be extremely good. Reading the slide from the top, from the bottom to the top, I checked this reference. It's actually still there. When I was preparing the lectures, I gained a lot of. I actually made a point of listening to this audio. So again, one can run an entire course or an entire semester course on GPU computing. There is a wealth of information available. A good starting point is the NVIDIA website. So there is the developer website. It's easy to get overwhelmed by the materials that are available there. There are the comparisons with the CPU, and I kind of agree with the 2010 paper there. One has to be careful. If you evaluate performance, it may be a lot better and much more honest to compare two different GPUs rather than comparing against a CPU, which is often not fair because of its multi-threading capabilities, and also with the fact that one has to consider often that one uses completely different algorithms in the end when one considered data parallelism. Okay, so this is a first lecture in a short sequence of 7 lectures that focus on GPU acceleration. So my hope is to give a brief overview of the essentials in a rapidly evolving, but still a very important pillar, even getting a more important pillar of high performance computing.